Well, I'm glad to see you back again. We're going to continue on our chapter on heat and the second law of thermodynamics, and in fact, we'll wrap up this topic in this lesson. To quickly review some of the major things we've talked about, we've explained the concept of heat, and we've talked about how heat flows from hot to cold. We then talked about the second law of thermodynamics, which essentially states that the universe becomes more disordered with time. We defined and explained entropy. We gave numerous examples of entropy. And we described how in natural processes there's always a tendency for things to spread out or become diffuse or to become degraded or dissipated. To express this in an extreme way, chaos is always at our heels. There's always a tendency for things to become more disorganized and disarray. That is a direct consequence of this second law of thermodynamics. With respect to the flow of thermal energy from hot to cold regions, we talked about the microscopic origins of this being related to the kinetic motion of atoms and molecules, and how the flow of thermal energy was really related to the dissipation of this kinetic energy of molecules from hotter regions to colder regions. But we also said that the reverse does not happen. That is, thermal energy does not flow from cold to hot. For example, if you have a bar of metal, thermal energy will not spontaneously separate into two sides, a hot side and a cold side. There is not a spontaneous separation of hot and cold regions in an object. Instead, thermal energy spreads out or dissipates in order to equalize temperature. In this lesson, we'll talk about how there is always a loss of energy in mechanical processes. Energy is always dissipated. It's always lost. It is one of the consequences of the second law of thermodynamics. But first, let's ask the question, how do we make something colder than its ambient environment? We just said that the second law tells us that there's not a spontaneous separation of hot and cold regions. But in fact, we know that the inside of a refrigerator is colder than the rest of our kitchen. So we know that even in our own apartments, we have regions where there is a segregation of hot and cold. Yet we've said that the second law says that this will not happen spontaneously. Well, yes, it will not happen spontaneously, but you can make it happen through the expenditure of energy. Now, refrigerators use a compressor, which we will not go into how that it works exactly, and they withdraw heat from inside the refrigerator, thus cooling things down. And of course, you have insulated walls of the refrigerator to maintain the cold inside once you have removed the thermal energy. So where does that thermal energy go? Well, that thermal energy from inside the refrigerator is actually pumped out to the rest of your room. And in fact, if you know about the coils in the back of a refrigerator, you know that actually a refrigerator puts out a lot of thermal energy to the rest of the room. So with an expenditure of energy, we can in fact create regions that are colder than the ambient conditions. Likewise, we can create regions that are more organized, more ordered. We can clean our room, but at the expense of doing work. So we can reduce entropy locally. We can reduce the kinetic motion of water molecules by freezing them into a solid or ice. We can do this locally with an expenditure of energy. And the second law tells us that when we do so, the entropy of the universe must increase. That is, achieving a local ordering of a system must be at the expense of increasing the disorder somewhere else. And that's because, if you note, when we've talked about the second law of thermodynamics, we've talked about the entropy of the universe, very large. The entropy of the universe is considered to be the entropy of the system, whatever it is we're focusing on, plus the entropy of the surroundings. So if in fact, through an expenditure of energy, we bring about a decrease in the entropy of a system, for example, inside of our refrigerator, lowering its temperature, freezing water to ice, we can lower entropy locally in our system if there is an increase in entropy in the surroundings. So if one goes down, the other must go up by a larger amount because the sum must be positive. There must be an increase in entropy of the universe in any spontaneous process. That is what the second law tells us. Now, some consequences. Now, a corollary of this second law is that you cannot construct an engine that does nothing but convert heat to useful work. Now, this is a little bit of a confusing way to state this, and I'm trying to give it to you in the way it was stated historically. What this really means is that you can't entirely convert energy, whether it be thermal energy, position with respect to gravity, chemical energy. You can't convert all of the energy available to do work. Some of the energy will always be lost as heat to the surroundings. With the first law of thermodynamics, we said that you could convert energy from various forms. Thermal energy to electrical energy, positional energy with respect to chemical energy, etc. We can convert energy between different forms. The second law says that when we do this, some of that energy is always degraded and lost as heat to the surroundings. Now, another way of looking at this is that it says that there cannot be a perpetual motion machine. And I show in the bottom right a drawing of what was suggested to be a perpetual motion machine back in the 12th century, something called Bhaskara's wheel. Now, it turns out that there have been hundreds or thousands of designs of perpetual motion machines, but none of them really work as perpetual motion machines. They all wear down because there will always be some friction, something that slows it down to keep such devices from running forever. And in fact, the U.S. Patent Office has received so many requests to grant patent for perpetual motion machines that they have a special form that you have to fill out because you have to actually demonstrate that it works. And there probably have been a few patents granted, but as you can tell, you can't go to Amazon or Walmart and buy a perpetual motion machine because they simply do not work. Why? Because of the second law of thermodynamics, because some energy is always wasted as heat in any process. Now that leads to a discussion of the efficiency of engines. A coal-fired electrical generating plant is about 40% efficient in converting the chemical energy of coal, when coal is burned, the chemical energy of coal to electrical energy. About 40% efficient. As you will see, that's pretty good. That's pretty high efficiency. Our internal combustion engines in our automobiles are about 18 to 20% efficient, with the best operating near 37% efficiency. Small electrical motors can be 30, 50, 60% efficient. Solar cells about 15% efficient, and the muscles in our bodies are about 14 to 27% efficient in converting chemical energy from our fuel molecules to mechanical energy through movement of our muscles. Why? Well, of course, because anytime we have components moving past each other, there will be friction, production of heat, which is just one way of explaining the consequence of the second law. You can either say heat is produced by friction, or also entropy is produced when things diffuse and randomize and become spread out. So a consequence, when we convert energy from one form to the other in an attempt to do work, there is always some energy that is wasted through production of heat, production of entropy. Some other issues involving the concept of entropy. If you major in computer science or mathematics, you probably will take classes discussing information theory with respect to computing, how this involves the organization, storage, and transmission of data. The concept of entropy is closely related to information and probability and statistics, as we discussed with respect to Ludwig Boltzmann and the equation entropy is equal to K times ln of W. You might also talk about entropy in classes involving cosmology. You may read about or hear about the heat death hypothesis of the universe, which is a consequence of the second law. You may also take courses in fields like economics and talk about the concept of entropy. In fact, there is sort of a subfield called thermoeconomics, in which the concepts of the first and second law are applied in economics. And since I have members of my family who have degrees in social work, I recall them talking about entropy in their field. And So I want to point out that in fields like sociology and social work, you'll also visit this concept. And I'll read for you the definition of social entropy. Social entropy implies a tendency of social networks and society in general to break down over time, moving from cooperation and advancement towards conflict and chaos. Oh boy, what we have to look forward to. If you major in biology or medicine, you may also discuss processes with an emphasis in entropy. For example, the aging process, how our bodies actually have a planned or programmed obsolescence called senescence, and you may also talk about the accumulation of junk DNA in our chromosomes. So these are a variety of topics that are related to the concept of entropy. Now, I want to wrap this up by essentially restating these two extremely important laws of the universe, the two fundamental theorems of mechanical theory of heat. These were expressed by Rudolf Clausius in 1865, and they are still essentially the way we phrase the first and second law of thermodynamics today. The first law, the energy of the universe is constant. We have only so much energy. That is, when the universe was created, it was endowed with so much energy. Second law, the entropy of the universe tends to a maximum. That is, there is this dissipation of energy leading to the production of entropy, and that this is an inevitable process, the second law of thermodynamics, that energy is always degraded, we always produce entropy. Okay, we're going to pause for a quiz, and this is the end of the chapter on heat and the second law of thermodynamics. We've covered concepts from Humpty Dumpty to Ludwig Boltzmann and Rudolf Clausius, and I hope you've enjoyed it.